Today what we're going to do is take a journey through time and space, and we're going to cross the seas of geography, history, and mathematics in the process. Did you ever wonder how Columbus actually got across the ocean to the New World? Did you ever wonder how Magellan actually sailed from Europe around Cape of Good Hope or Cape of Horn and ended up in the Pacific? How did these sailors know where they were going and what they were doing? So let's start with a little background, and then we'll try to answer those questions. And in the process, we'll sneak in a handy formula that you can use later on in life to figure out all kinds of interesting things. Okay, you're all the crew here, and I'm supposedly the skipper or the captain of the ship. Now, in order to get things going, we can't all be up on watch at the same time because we're going to get tired. So we need to devise a system to allow some people to be up doing their duties and other people to be resting. So, as with most things that are nautically related, there's a long tradition as to how this is done. So I'm just going to explain what the tradition is. The nautical day starts at noon on one day and goes to noon on the next. And it's divided into 4-hour watches because 4 hours is about the maximum amount of time a person can really pay attention to a demanding, specific job without losing concentration and so forth. So we're going to have a watch that'll run from noon for 4 hours. We'll call it the afternoon watch. Then we're going to have another watch that'll go from 4 o'clock in the afternoon to 8 o'clock in the evening. We're going to call that the dog watch. And there's a lot of jokes about why it's called the dog watch, but for our purposes, let's just say by the end of the day, you're going to be dog tired. Okay, after that, we're going to have the evening watch, which is going to take us up until midnight. From midnight to 4 in the morning, we're going to have the mid-watch. From 4 in the morning to 8 in the morning, we're going to have the morning watch. And from 8 o'clock until noon, until just before noon, we're going to have the
forenoon watch.
All right, very good. Okay, so we've got this divided in 4 hours apiece. Now, you'll have this watch and you'll have that watch and so on. Now, why do you think the nautical day runs from noon to noon? Why not midnight to midnight the way we do it, in modern times today?
Because of the sun is directly overhead at noon?
Well, but why is that? You're on the right track. You're very close to the right answer. Why, though, don't we start it at midnight? We're Columbus. How are we going to tell when midnight comes? Are we going to whip out our Timex and go, oh, gee, must be midnight time to start a new logbook? No. But we can tell when noon comes. How are we going to know when noon comes? You're on the right track.
Well, it has to do with the sun.
Exactly. And the sun does what in the morning?
It rises and
What's it do in the afternoon?
fall.
And what's it do at the highest point? Sits there for a
Straight
moment.
overhead.
Sits there for a moment, right? Not necessarily straight overhead, but it gets higher as the morning goes along. It hangs there for a moment, and then it starts on down. So how are we going to know when this magic moment called noon occurs?
I'd say still, one's there.
Well, but, we're the ship's bobbing up and down. How are we going to know when this has reached that magic point and started back down again? Suppose we had a way to measure the angle of the sun. And in the morning, the angles would be getting higher, and in the afternoon, they're going to be getting lower. So how are we going to measure angles? How about something called a sextant? Okay, would you like to come on up here? You drop this, you're dead. Put your right hand there, okay? Look through the eyepiece. And I'm just going to manipulate this for you, but basically what you see is a split image. You see a right half and a left half. And suffice it to say that at 0 degrees of elevation, both halves should have, if you see a horizontal line out there, they should be pretty closely lined up. Okay, thank you very much. We successfully completed the mission. And during the day, what we would do is, we would know roughly when noon is going to come. That's just sort of common sense. But when we want to get it right down to the moment, we're going to go out there with the sextant, and we're going to measure the angle and write it down, measure the angle and write it down. And when the numbers stop getting bigger and kind of stay the same for maybe a minute and then start going back down, we're going to call that noon. So at that point, we have a very demanding job. Who would like to volunteer for a very demanding job? Okay, great. You're going to turn the hourglass over for us.
Excellent.
And it's going to take 30 minutes for the, go ahead and flip it. It's going to take 30 minutes for the sands to run from the top to the bottom. And what would be a good thing so that everybody who's on watch and has put in a half an hour of work know that, hey, half an hour's gone by. What's a good way to do that?
Ring a bell.
Let's ring a bell. Okay, so Unfortunately, it's going to take 30 minutes for that to go down, but let's assume that it has gone down once. We're going to ring a bell. And so it just goes, ding, and you flip it. And at the end of the second half hour, how many bells would we ring? Two. We go ding, ding. Okay? And at the end of the third half hour? 3 bells. Okay, now, sometimes you go ding, 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 ding. It's hard to tell, how many dings there were. So we're going to ring them in groups of 2. So for the third hour, or third half hour, we're going to go ding, ding, and then a ding. And then eventually you have ding, 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 and so on. And eventually at 8 bells, you'll have eight bells. So basically every bell is half an hour. So we know as the rest of us are up there on the sails and we're on lookout, we're doing all these jobs, we're going to be listening for those bells. And when 8 of them have come by, we're off watch and the new guys come up and it's their turn to deal with all this. So basically, that's why you have 4-hour watches. That's how ship's bell time works. Now, if I were to tell you that we sighted a mermaid at 3 bells, what time of day did we sight the mermaid? Well, it'll be how many half hours into a watch? 3 bells. 3 half hours, so it's an hour and a half. Without more, you don't know, did we find it 3 bells here, here, here? So to actually tell ship's time, you need to also say in the watch. At 3 bells in the dog watch, we sighted the lighthouse. That way we know exactly 3 bells in the dog watch would start at 1600. An hour and a half would be 1730. So at 5:30 in the afternoon, we sighted the lighthouse.
Why would you do a half an hour instead of an hour?
Wouldn't you like to know more frequently how much longer you have to stand your watch? Don't you, when a class gets boring, start to look at that little watch?
I guess that's just really complicated when it could just be 1 bell's an hour, 2 bells, 2 hours, 3 bells. I'm a very simple person.
Well, that's fine. On your ship, you can do it that
Okay.
way.
I was just curious if
Every
there was
other
a
ship I've
big
ever heard
purpose.
about in history, including the U.S. Navy and the Royal Navy, this is the
Huh.
way they've done it for centuries. Okay,
Okay.
so now we've got the ability to track time. Now, that's one of the equations in our little formula here. We got the time down. Now, the question is going to be, to some extent, how fast are we going? If we're sailing from Spain to get to the New World, we'd like to get there somewhat quickly, and we need to figure out a way to know how fast we're going, okay? This is our ship. Ship's going that way. Anybody got a bright idea how we can tell how fast the ship is going? The ship, by the way, is 100 feet long, because we measured it long. It's 100 feet long. So how are we going to tell how fast this ship is going? Ideas?
Well, if you threw something out the front of the ship.
All right.
and walked-
Exactly. So here's my floating piece of chalk, and we're going to have, in addition to the standard hourglass, which is 30 minutes per side, we're going to have a very short glass, which will actually enable us to pick up just a few seconds. We're going to drop something off the bow of the
We
boat.
could throw Sarah off the front and watch how long.
Throw Sarah, she's going to help. As the boat goes past, the sands are running, and by the time we get to the back end of the 100-foot boat, we mark the time, and now we know that the boat has gone 100 feet in X number of seconds. So you can work your calculation out to say, okay, this is how fast the ship is going. Generally speaking, in the old days, sailing ships that you're familiar with went something on the order of 6 to 10 knots, depending on the wind and the waves and so forth. Now, what's a knot? Why don't we say at 6 miles an hour? What's the difference between 6 knots and 6 miles an hour? Okay. On a chart, and I forgot to bring in a beautiful chart of the world, we have something called latitude. And latitude is divided into how many degrees from the equator to the North Pole?
180.
Well, it's 180 from pole to pole. How many is it from the
90.
equator north? It's 90, okay? And those 90 degrees are broken down into what subpart?
Minutes and seconds.
Minutes, okay? There's 60 minutes in each degree. And how many, 60 minutes in each degree, and how are minutes broken down?
Seconds?
60 seconds, okay.
Oh, man.
So basically, what happens is on a nautical chart, if you look over at the latitude side of the chart, and latitude goes which way? Show me with your thumbs. Does latitude go up and down or left and right? We'll do a thumb check here.
What do you mean, go?
Oh.
You mean, is it,
Is latitude measured up and down, or is latitude measured?
oh, it's a measure.
So what is the measure?
Realistic.
Okay, we have some different opinions here, okay? The answer is
How does
latitude.
that matter? You go,
Latitude is measured north and south of the equator, and longitude is measured east and west of the equator. Okay? And
Still get mixed up.
if we have 90 degrees of latitude, I'll close this lid so you can see better. If we have 90 degrees of latitude from the equator to the North Pole, and each one of those is divided down into, let's just say, for example, this was 40 degrees north, and if this was 39 degrees north, we would have how many minutes between there? From 39 to 40, 1 degree is how many minutes? You had the answer a minute ago. 60, okay. So what's going to happen is, mariners by convention will call those 60 minutes 60 nautical miles. So basically, the answer is that 1 nautical mile equals 1 minute of latitude. And the reason why that's really neat is that you can then measure distance right off the chart. You can go from here to here, you put your dividers on the distance, you know, between the two objects, go over to your latitude scale, and there's your distance in miles. It's really simple. Okay, now, we're going to sail from the New World, are we going to sail from the Old World? We're going to go to the New World. We know that we've measured our ship. We know that our ship, will make this real simple, our ship is going to do 10 knots. Oh, I forgot one part of this, to get to the knots part. A knot is 1 nautical mile per hour. So basically, the simple part of this is that a statute mile on land is 5,280 feet. A nautical mile, since it is 1 degree of latitude, is equal to 6,080 feet. So a nautical mile at sea is a little bit longer than a land mile. Now, you don't need to obsess and get, you know, oh my gosh, is this going to be on the final or something like this. Just know that a nautical mile is a little bit bigger than a land mile. So if you're doing 10 nautical miles per hour, you're doing a little bit more than what you would be doing in a car. So 10 nautical miles per hour is probably something like 12 or 13 miles per hour in the car. Okay, now, we want to sail from the Old World to the New. We're going to go out across here. We have our timekeeper. We're measuring our altitude. We know when noon comes each day. And what we want to avoid doing, of course, is we're sailing at night. We're Columbus and so forth. What kind of lights do we have on this ship, if any? Perhaps some sort of whale oil lamp or a candle or something like this. We're not going to have big floodlights and so forth. So one of our concerns is going to be, as we're sailing along, we don't want to bump into the New World in the middle of the night, have a ship run aground and wake everybody up and get wet feet and swim to shore. So how can we get some indication of, okay, we know it's a long way and we know it's going to take several days to get there, but once we've been out there several days, how do we know we're not going to bump into Virginia in the middle of tonight and ruin our watch? There's an old Navy saying, a collision seat can ruin your day. How are we going to make sure we don't bump into Virginia tonight? Ideas. We've been out there a long time. Okay, well, this is what we're going to do. We're going to keep track of our progress as we go. If this is, someone the other day did a very beautiful depiction of the Iberian Peninsula. So we'll say that this is Spain. And we know that somewhere out here, we don't know quite where, is some unknown land that we're sailing to. But we know it's kind of a long way off because up till now, no sailor's ever been there and come back that we know of and has told us about it. So we're going to start sailing across. If we know what time of day we started, and let's say we left at noon on Monday from Spain, and we know we're doing 6 knots, 6 nautical miles per hour, if this is day 1, where should we be at noon on day 2? Doing 6 nautical miles per hour, 24 hours.
What's the question?
The question is, if we sail from Spain at noon on day 1 and we do, let's just make this easy, 10 knots, how many miles will we have covered in the first 24 hours? 240 miles. Okay, nautical miles. Okay. So So what we're gonna do is we're just gonna keep track of our progress as we go across here. And now you know how to compute the speed of the boat. So if our speed slows up or speeds up, we can compensate for that. We know how our time is running because every day we're going out at noon and we're marking our days off. So once we start getting over here, we're gonna have some idea of, you know, when we should be striking land. What's another feature? Now we're gonna get into oceanography a bit. If this is the water here, and this is Spain, how deep's the middle of the ocean, in just simple terms?
Really deep.
Very deep, okay. And what's gonna happen as our little ship starts getting closer to land here? The ocean bottom is going to get less deep, shallow, okay? How can we measure? In the middle of the ocean, we can't measure, but how can we measure once we think we're starting to get close?
Oh, anchor.
Drop a weight on a rope. Take a 300-foot rope, tie a big lead weight on it, drop it off. If it doesn't hit the bottom, we know the bottom's more than 300 feet away. We do this periodically, and for days and days and days, we've gotten no bottom. And now all of a sudden we start getting 300 feet, 290, 250, 180. What's that telling us?
Land.
We're getting close to land. So either we better just take the sails down and wait until morning so we can see what we're doing, or we better have a very, very good lookout, you know, as we get in close to land. Okay. Now, let's review a little bit on the D equals RT, and then we're going to go on to the next part. Okay. D stands for distance. Okay. R stands for rate. And T stands for time. Okay. T, I, and D. Okay, so now you know how to compute basically the elements of navigation. And what we're going to do now is we're going to do some time travel. We're going to go forward from the time of Columbus and Magellan and those guys. We're going to get down to the modern day and age. What we did there, as you can see, would be very complicated, and it would take a person called a navigator on the ship most of his or her waking hours to keep track of all this as we're going on, constantly measuring the speed, updating the chart, keeping track of the time, and so forth and so on. Nowadays, all that is done in this little gizmo right here, which is called a GPS unit. And this little unit is a receiver. And what it does is it receives a signal from satellite, make sure it sets this down. That it receives a signal from satellites that are passing around the Earth, and it knows where the satellites are supposed to be, and it knows that it should receive a signal at a certain time, and if it receives it at a different time, that's because of the time it took the signal to travel from the satellite to the unit. So what that is really a giant mathematical computer, and if it knows the distance to that satellite is such and such, and the distance to this other satellite is something else, and the distance to that one, and got 12 satellites there, there's only one place on the Earth where all those things can be happening at exactly the same time. And so that's how it knows where we are. So we've come from the days of very, very complicated procedures to push a button.
Do you want us to pass it around?
Oh, sure. But when you talk about pass around, what happens if somebody drops that overboard? We got a problem. So you've got to know, if you're actually going out to sea, you've got to know how to recreate this stuff if push comes to shove. Your batteries wear out, it gets saltwater corrosion, you know, who knows what. So let me just show you one or two other things real quick, and then we'll wrap it up. The other thing that you can do with, we knew how to figure out when noon was. How can we use the knowledge of noontime to figure out our latitude north or south of the equator? You think about that for a moment.
I didn't hear the question.
Oh, if we know when noon is, because we've gone out and measured each day, how can we take that knowledge of noontime and convert that to latitude?
Well, the higher the sun, you're going to have to be between the two tropics somewhere.
Exactly, Tropic of Cancer, Tropic of Capricorn. We know basically that in the summertime, generally the sun is higher in the horizon at noon than it is in the winter. And so if we had a chart that basically said, on any given day of the year,